Welcome everyone to day 2 of classical mechanics. In this video, we are going to discuss solving differential equations. Differential equations numerically. And in fact, to do this numerical solution, we will be using a computer program. So let's write computer program. And my choice for this video is Python. It has a very user-friendly interface, and that's one of the reasons why we're going to be using it to write a program to solve a differential equation that we might encounter in a physics problem. Okay, so the first half of the video is me explaining the physics, and the second half we're going to actually code some program to solve a differential equation numerically. Now, let's consider a simple setup. Let's say that we have a spring mass system. This is M, this is K. We could write the Newton equations for this in a fairly simple manner. Let's do that. So we know that F is equal to ma. The force is going to be negative kx. Let's say that the spring is a Hookean spring, so it obeys Hooke's law. This equals m, and a is just the second time derivative of x, so it is x double dot. We then have mx double dot plus kx equaling 0, which is of course the same thing as this business. And oftentimes we define k over m to be omega squared, and we write this equation as this. X double dot is equal to negative omega squared x. Okay, this is one way of expressing the situation. And if you know some physics about oscillation, you might recognize that this is a simple harmonic motion. So we know that. Now, with that being said, let's solve this symbolically. Let's solve this the usual way, and then I will explain how we could solve this numerically. And, I mean, you could think about it, but a solution to this equation, the general solution is x is in the form some amplitude times cosine of omega t plus some phase shift. And I mean, you don't need to believe me. Let's see whether or not this solution satisfies the equation. So if we take the first time derivative of x, it's going to be negative omega a sine of omega t plus some phase difference, phi. And if we take the second time derivative, it's going to be negative omega squared a cosine of omega t plus phi. As you can see, this part is x of t. So what we have is the acceleration is equal to negative omega squared x. That means that in fact the equation satisfies it. Okay? So this is the solution basically. Now, if I were to give you some initial conditions, let's say that, I don't know, I tell you that x at time 0 is 5 meters, let's say. So this means the spring is stretched 5 meters from its equilibrium position. The spring is stretched 5 meters from its natural length. And I say that the speed, the velocity, initially is 0. These are the two information that I give you. And we also know that this is how the system behaves, how it changes over time. So using this, let's just substitute for, let's just basically make this simpler. Okay, let's find what a is. And if you look at it carefully enough, you can notice that, and then I also need to give omega, right? Let's say that, let's say that the mass is 10 kilo, let's use nice numbers. So if mass is 100 kilograms, I'm trying to make it nice, and hold on, let's do it like this. I am fixing the values. Let's say that the spring constant is 1,000 newtons per meter. And let's say that the mass is 10 kilograms. So when we do that, K over M is 100 with the units, of course. So then omega turns out to be, 10 radians per second. Did I get that right? Let's see. So yeah, that's right. So we know this as well. We described all the things about our system. And so I can now solve for x of t. I can write the specific formula. It's going to be 5 cosine of 10t. Right, if you write 0 here, that's going to be cosine of 0. That's 5. It satisfies the first initial condition. And for the second one, if we use this one, that one, you're going to see that we have negative 50 sine of 10t, right? And if I plug in 0 here, sine of 0, well, that's 0. So we also satisfied the second condition. Cool. Nice. This was just preparation for what we're about to do. If I were to ask you, what is the x position? So x position when t is equal to 5. What would you do? You would basically plug in 5 for the t here, right? And that would give 5 cosine of 50. And let's calculate what this is equal to. I'm going to grab my calculator. I will open my computer actually and use my calculator there. So I'm doing the calculation. Sorry for the delay. So 5 times cosine of, and this is in radians, 50. Cosine of 50. This is approximately, according to my calculator, 4.8 to 4830. Okay? Cool. Now the thing is, I did this physically. I arrived at this equation. But what if I don't know how to arrive at it? What if I am only given this information which describes how the system changes? So this describes how the system changes. This is a characteristic of the system. So let's write characteristic, a characteristic. I think I spelled that wrong. Who knows? Characteristic of the system. That's the characteristic of the system. And these are telling us how the system starts. How the system starts. So look at this. I mean, when you think about it, I know how the system starts. I know how it changes. I also know the characteristics of the system. So I should be able to find out what the position is going to be after 5 seconds. Can I do that without explicitly solving for this expression? Because even though it was easy in this case, maybe in some other problem I am unable to solve for the position. It's a hard problem maybe. And sometimes some differential equations, they are not solvable. You can't solve them symbolically. You must solve them numerically. So we will now describe a method for that. And then we will code it up. Now, the first realization comes from the fact that I could use the initial conditions to guess the next condition. So I can use the initial state of the system to guess the next state of the system. How do I do that? Well, if I know that the velocity, the time derivative of position, it is approximately equal to some change in the position divided by some change in the time, right? If I am limiting myself to very tiny changes in time, let's call that epsilon. This epsilon is a positive tiny change in the time. And if I am interested in this little time interval, then there's going to be a correspondingly little change in the x position, which I can express as x of t plus epsilon minus x of t, right? So if I solve for this, which is the next state of the system, you can see that I'm going to just solve for it. Let's see, it's going to be x of, and this is well, this is approximately, but, well, let's write it that it's approximately x of t plus epsilon x prime of t, right? And this is cool because I can choose what epsilon is. I can say that this is going to be 0.001 seconds, let's say. And I know the initial velocity, it was 0. I know the initial position, it was 5. So I guessed what the next position needs to be. It's going to be 5. That's how I can do it. But you notice something perhaps. The value didn't change because the speed, the velocity was 0 initially. We also need a way to update the velocity. How do we do that? We do that by considering this. Now let me go back a bit. Okay. How do I do that? Well, I also know what x the double prime is. It's going to be similarly the change in the velocity divided by some tiny time interval, which is epsilon again. So we now have an expression for the next velocity. The velocity at time t plus epsilon. It is the starting velocity plus the tiny change in the velocity. And now I can change the value of the velocity as well, which I can then use here to find different values for the position. And I am saying this because the acceleration isn't 0 initially. What is the acceleration? We have a formula for it in terms of the system gave it basically. It is equal to negative omega squared x. Okay? So using this information, I can repeatedly do this on and on and on again until this t plus until this t plus epsilon gives 5. When it is 5, I will stop the procedure, and at that point I will look at the value of x. This might sound all abstract, but let's in fact code this, and once we code the program, you will see that it works out. Also, keep this value in mind. The program should give us this value. If it doesn't, well, we coded it up wrong then. Okay? So see you in the programming part. Okay, welcome to the programming part. I am using a website called Replit to write my program, and I will attach the link to it. And I'm not sponsored or anything. I've been using this for years now, and I think I should also use it to write this simple program, okay? So. Cool. Now, this is Python, and it is a very useful programming language to start learning if you're very new to it, because it has a user-friendly interface. I will first start by defining the initial conditions of the problem. I will use x for the position, and we said that was 5 meters, right? I'm just writing 5, but there is a unit, of course. But here, well, we can't write the unit. It's just going to be 5. And I also told you that the initial speed was 0, which I will denote with x1. x1 here refers to the fact that velocity is the first time derivative of position. So this is 0, as we said. And also, well, we could also write omega maybe. Well, we don't really need the omega. We can write it inside the program. Okay. So this is it. And as we talked like a minute ago, we are going to do a repetitive and iterative process. We're going to iterate until time is 5. So I will say, I also need to define a time then. So t is going to be time, it is 0. And so I will say while time is less than 5, we're going to do something. So as long as time is less than 5, this program is going to continue working. And I also need a step size. I forgot that. So we talked about epsilon, right? Let's use E for that. And we need to choose a very small step size for better answers. Let's use 0.001, let's say, initially. Okay, this is a small number. This is seconds. Again, we can write the unit here. So, well, okay. In this while, we basically want to update our system. We're going to update the state of our system until time is equal to 5 seconds. And once that happens, the update will stop and we will get the value of position at that point. That's the question, basically. So, for that, we already know what the acceleration is, don't we? If I define the second time derivative, the acceleration, to be, and we know from the physics of it that it is going to be negative omega squared x, and we chose omega to be 10, so we're going to write negative 100 times x. This is what we know from Newton's law, basically. This is what we derived physically, like 5 minutes ago. Okay? Now, this is enough to update the acceleration, but we also need a way to update the position. To do that, we're going to use the formula that we discussed, which comes from the definition of velocity. The x value is going to be the previous x value plus the change in the time, so e times the velocity, x1. Okay? And don't get confused about this. You know, you have x equaling x plus e times x, x1. This doesn't mean, you know, you can't put this x to the other side. This is not an algebraic equation. This only means that you're updating the value of x by increasing it with e times x1, the change in the position, okay? This is notation, basically. And we also need to update the velocity. And in fact, the AI is even suggesting me what to write. And that is the thing that we're going to write. x1 is going to be the current value of x1 plus the time interval times the value of the acceleration. Okay? And this is it, in fact. Once this while is done, once this while loop, they call it, is done, I will use an unindented, right? This is like there's a indent here, indentation there. I will use an unindented line to do something outside of the while loop, and I will do a print. This just prints the value to the screen right here, to the right part, and I will print the value of x. So hopefully we get some value that is close to what we found 5 minutes ago. Let's see. If I run this program, let's see what we get. We're going to get, it's taking some time, sorry about that. It is taking longer than I expected. It takes usually much less time, but we'll see. Oh, sorry, it takes forever. I did something very wrong. Excuse me for that. Now, inside the while, we need to update t, right? If it is 0 all the time, it's going to be less than 5, always. So we need to update it. T is going to be increased by the value of epsilon for each iteration. That's why we didn't get the result. It would take forever. Okay, now it should work out. Much faster, I think. Yes. And the value is this. We had found the value to be, I will write what we found physically. We found it to be 4.82, 4830 using our physics knowledge and math knowledge. This is very close to it. What if I make the step size even smaller, like this? I should get closer to it. Do I? And yes, I do, as you can see. This is much closer to the actual value that we found using physics. And in the limit, as epsilon goes to 0, we get exactly this value. And something to note here, the order in which you update these three values, the position, the velocity, and the acceleration, it doesn't matter. I can, write this here, let's say, and I will still get the same result. Or something very close to it. Let's see if I do. And as you can see, it is a bit different, but it is still very close. And the reason is, since we are dealing with very small changes in time, it doesn't really matter if you're updating one of them before the other. There is a very small difference. And in the limit, that difference does not exist. it is happening all simultaneously, let's say, instantaneously. And that is the magic of calculus. It helps us describe instantaneous changes. Anyways, this is it for this video. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.